This is an FRQ question from 1994 from AP Physics B. Now these sections are covered in AP Physics 2. So a point of source S of monochromatic light is located on the bottom of a swimming pool filled with water to the depth of 1 meter, as shown in the picture. And the index of refraction of water is given 133 for this light. And then point P is located on the surface of the water directly above the light source. A person floats motionless on the raft so that the surface of the water is undisturbed. Determine the velocity of the source light in the water. For this problem, I have to remember what index of refraction means. So the index of refraction is equal to the speed of light in the vacuum over the speed of light in the medium. So if I want to find out what the speed of light in the medium is, I'm going to solve for V. That's going to be the speed of light in the vacuum divided by the by the refraction index. And I'm going to get 310 to the 8. The speed of light divided by 1.33, and that will give me 226 10 to the 8 meters per second, the velocity of the light in the pool water. For the next question, they say that on the diagram above, draw and approximate the path of the ray of the light from the source S to the eye of the person. It is not necessary to calculate any angles yet. So when the light is coming from the source, it's coming from more dense medium to less dense medium. So when the light is, I'm going to start with a person's eye. So if the light is coming to the person eye from somewhere right here, then if there was a normal line at this point where the light is gonna come out, then the source of the light would be coming from this point. And then what's interesting to notice is that index of incidence in this case is going to be smaller than the index of refraction. And that happens because the light in the water travels slower than the light travels through the air. For the next question, they ask you to find the critical angle for the air-water interface. To solve this question, I will have to use the Snell's law. So you would have index of refraction in the water times the sine of the angle in the water is equal to index of refraction in the air times the sine of the angle of refraction in the air. So if, I'm going to redraw it right here. If the light was, the source was at this point at the bottom of the pool, and we're going to have the dotted line right here. Here is the eye of the person, and the light is coming like that. Then this would be the index of incidence, and this would be the index of refraction. So this is theta A, air, and this is theta W for the water. And because they say the angle is critical angle, that means when the ray reaches the surface, it doesn't pass to the surface. It stays within the water. In the angle of refraction, this angle would be 90 degrees. So for 90 degrees of the angle of the air gives me a 1, and the index of refraction for air is also 1. So on this side, I would have a 1 because sine of 90 is 1, and index of refraction for the air is 1. And then index of refraction for water is 133, and this is the angle of incidence that I am looking for. So sine of theta in the water is equal to 1 over 133. And if I want to find this angle, the critical angle, I have arc sine of 1 over 1.33. And that gives me the angle of 48.7535 degrees, or 48.75 is okay. So that was the answer for C. And now for our next question, they say that suppose that a converging lens with a focal length of 10 centimeters in water is placed 20 centimeters above the length of the surface. So they show you 20 centimeters. It's above the ground, as shown in the diagram. And then an image of the light source is formed by the lens. And so for the next question, they ask you to calculate the position of the image with respect to the bottom of the pool. So what I have is the focal length is 10 centimeters and the distance to the object, which is the source of the light, is 20 centimeters. I'm going to scroll a little bit down so we can have working space to work out the D part. So to calculate the position of the image, I have to use the lens equation, which is 1 over the focal point is equal to 1 over the distance to the object plus 1 over the distance to the image. The focal point is 10 centimeters. I can leave it in 10 centimeters or in centimeters because my answer is going to come up as in centimeters as well. I don't have to convert into meters. And the distance to the object is 20 centimeters. And then plus 1 over di. I'm going to times each fraction by 20 to get rid of the denominator. So if I times the first one by 20, I get a 2. The second by 20, I get a 1. And the third one by 20, I get 20 over di. So di is going to be equal to 20 centimeters. So if the light is 20 centimeters below the lens, the image will appear 20 centimeters above the lens, or 40 centimeters above the surface. And because they ask me calculate the position of the image with respect to the bottom of the pool, my answer in this case is going to be 40 centimeters above the pool. Or to be exact, it's above the pool, the bottom of the surface of the pool. And then for the last question, they say if instead of the pool were filled with a material that is different index of refraction, describe the effect, if any, on the image in its position in each of the following cases. And so the first one, they say index of refraction of the material of the pool that filled in it with is equal to that of the lens. So if the index of the refraction of the material that this pool filled in with is equal to the index of refraction of the lens, then the wave would not refract going from the pool material to the lens. So the light in this case would not bend, and you would not even know that the lens is inside of that material that the pool is filled in. So the light would pass through the lens and through the material that the pool is filled in with, and creates no image formed by the lens. And for the second part of this question, they say if the index of refraction of the material was greater than the one of the water, but less than the one of the lens. So in this case, when you decrease the difference of index of refraction between the lens and the surface, which is the material that the pool is filled in with, then there will be less bending as the light passes through the lens. And this will move the focal point farther away from the lens, and the image that would be created by this lens in that material would be also positioned farther away from the surface of the pool or from the bottom of the pool. So that is all I have for this question, 1994 AP Physics B exam FRQ question. And thank you for watching, and I hope I see you in my other videos.